Hello students, welcome to the lecture on Object Relational Database, and after this lecture we will be able to learn the following objectives. Understand the concept of database system architecture, discuss about centralized systems, describe the parallel databases, understand the concept of input-output parallelism, and explain the inter-query parallelism and inter-operation parallelism. Let us start with database management systems. Database management systems, DBMSs, are complex, mission-critical software systems. Today's DBMSs embody decades of academic and industrial research and intense corporate software development. Database systems were among the earliest widely deployed online server systems and as such have pioneered design solutions spanning not only data management but also applications, operating systems and networked services. The computers have evolved from big mainframe computers to small desktop personal computers. The advances in computer and its architecture have also resulted in the advances in databases and its architecture. Here we discuss the architecture of databases of three kinds: centralized DBMS architecture, client-server architecture, and distributed databases. Centralized systems run on a single computer system and do not interact with other computer systems. General purpose computer system, one to a few CPUs and a number of device controllers that are connected through a common bus that provide access to shared memory. Single user system, example, personal computer or workstation. Desktop unit, single user, usually has only one CPU and one or two hard disks. The OS may support only one user. Multi-user system, more disks, more memory, multiple CPUs and a multi-user OS. Serve a large number of users who are connected to the system via terminals, often called server systems. Client-server model. The client-server model distinguishes between applications as well as devices. Network clients make requests to a server by sending messages, and servers respond to their clients by acting on each request and returning results. One server generally supports numerous clients, and multiple servers can be networked together in a pool to handle the increased processing load as the number of clients grows. This is the process which typically makes a request for information. After getting the response, this process may terminate or may do some other processing. Run own copy of an operating system. Run one or more applications using the client machine's CPU, memory. Application communicates with DBMS server running on server machine through a database driver. Database driver, middleware, makes a connection to the DBMS server over a network. Examples of clients: PCs with MS Windows operating system. Forms and reports developed in Power Builder, MS Access, Borland Delphi, Oracle Developer, MS Visual Basic, Java, C# or C++, etc. This is the process which takes a request from the clients. After getting a request from the client, this process will do required processing and will gather requested information and will send it to the requester client. Once done, it becomes ready to serve another client. Server process is always alert and ready to serve incoming requests. Run own copy of an operating system. Run a database management system that manages a database. Provides a listening daemon that accepts connections from client machines and submits transactions to DBMS on behalf of the client machines. Examples: Sun Spark server running Unix operating system. RDBMS such as Oracle Server, Sybase, Informix, DB2, etc. Intel CPU based server with Windows Server operating system running MS SQL Server. Database functionality can be divided into backend. Managers access structures, query evaluation and optimization, concurrency control and recovery. Front end consists of tools such as forms, report writers and graphical user interface facilities. The interface between the front end and the back end is through SQL or through an application program interface. Processing of the entire database system is spread out over clients and server. DBMS can achieve high performance because it is dedicated to processing transactions, not running applications. Client applications can take full advantage of advanced user interfaces such as graphical user interfaces. Implementation is more complex because one needs to deal with middleware and the network. It is possible the network is not well suited for client-server communications and may become a bottleneck. Additional burden on DBMS server to handle concurrency control, etc. As more business rule logic is programmed into the client-side applications, they can become unwieldy. Stored procedures and triggers can help in this case. Two-tier architectures. In this architecture, client directly interacts with the server. This type of architecture may have some security holes and performance problems. Internet Explorer and web server work on two-tier architecture. Here, security problems are resolved using Secure Socket Layer SSL. Three-tier architectures. In this architecture, one more software sits in between client and server. This middle software is called middleware. Middleware are used to perform all the security checks and load balancing in case of heavy load. A middleware takes all requests from the client and after doing required authentication, it passes that request to the server. Distributed system. Data spread over multiple machines, also referred to as sites or nodes. Network interconnects the machines. Data shared by users on multiple machines. Homogeneous distributed databases. Some software schema on all sites, data may be partitioned among sites. Goal. Provide a view of a single database, hiding details of distribution. Each site surrenders part of its autonomy in terms of right to change schemas or software. Appears to user as a single system. Heterogeneous distributed databases. Different software schema on different sites. Difference in schema is a major problem for query processing. Difference in software is a major problem for transaction processing. A local transaction accesses data in the single site at which the transaction was initiated. A global transaction either accesses data in a site different from the one at which the transaction was initiated or accesses data in several different sites. Sharing data. Users at one site able to access the data residing at some other sites. Autonomy. Each site is able to retain a degree of control over data stored locally. Higher system availability through redundancy. Data can be replicated at remote sites and system can function even if a site fails. Disadvantages. Added complexity required to ensure proper coordination among sites. Software development cost, greater potential for bugs, increased processing overhead. Atomicity needed even for transactions that update data at multiple sites. The two-phase commit protocol 2PC is used to ensure atomicity. Basic idea. Each site executes transaction until just before commit and leaves final decision to the coordinator. Each site must follow decision of coordinator even if there is a failure while waiting for coordinator's decision. Parallel databases. Prices of microprocessors, memory and disks have dropped sharply. Recent desktop computers feature multiple processors, and this trend is projected to accelerate. Large volumes of transaction data are collected and stored for later analysis. Multimedia objects like images are increasingly stored in databases. Large-scale parallel database systems increasingly used for storing large volumes of data, processing time-consuming decision support queries, providing high throughput for transaction processing. Parallel database systems consist of multiple processors and multiple disks connected by a fast interconnection network. Data can be partitioned across multiple disks for parallel input-output. Individual relational operations, example, sort, join, aggregation, can be executed in parallel. Data can be partitioned and each processor can work independently on its own partition. Queries are expressed in high-level language SQL translated to relational algebra. Makes parallelization easier. Different queries can be run in parallel with each other. Concurrency control takes care of conflicts. Thus, databases naturally lend themselves to parallelism. Input-output parallelism. Reduce the time required to retrieve relations from disk by partitioning the relations on multiple disks. Horizontal partitioning. Tuples of a relation are divided among many disks such that each tuple resides on one disk. Partitioning techniques. Number of disks is equal to n. Round robin. Send the ith tuple inserted in the relation to disk I mod n. Range partitioning. Choose an attribute as a partitioning attribute. A partitioning vector VO, V1, Vn2 is chosen. Let V be the partitioning attribute value of a tuple. Tuples such that Vi is less than equal to Vi plus 1 go to disk I plus 1. Tuples with V less than V0 go to disk 0 and tuples with V greater than equal to Vn2 go to disk N1. Evaluate how well partitioning techniques support the following types of data access: scanning the entire relation, locating a tuple associatively, point queries. Example, RA is equal to 25, locating all tuples such that the value of a given attribute lies within a specified range, range queries. Example, 10 is less than equal to R, A is less than 25. Good for sequential access. Assuming hash function is good and partitioning attributes form a key, tuples will be equally distributed between disks. Retrieval work is then well balanced between disks. Good for point queries on partitioning attribute, can look up single disk, leaving others available for answering other queries. Index on partitioning attribute can be local to disk, making lookup and update more efficient. No clustering, so difficult to answer range queries. Range partitioning provides data clustering by partitioning attribute value. If a relation contains only a few tuples which will fit into a single disk block, then assign the relation to a single disk. Large relations are preferably partitioned across all the available disks. If a relation consists of m disk blocks and there are n disks available in the system, then the relation should be allocated min mn disks. The distribution of tuples to disks may be skewed. That is, some disks have many tuples while others may have fewer tuples. Types of skew. Attribute value skew. Some values appear in the partitioning attributes of many tuples. All the tuples with the same value for the partitioning attribute end up in the same partition. Can occur with range partitioning and hash partitioning. Partition skew. With range partitioning, badly chosen partition vector may assign too many tuples to some partitions and too few to others. Less likely with hash partitioning, if a good hash function is chosen. To create a balanced partitioning vector, assuming partitioning attribute forms a key of the relation, sort the relation on the partitioning attribute. Construct the partition vector by scanning the relation in sorted order as follows. Alternative technique based on histograms used in practice. Balanced partitioning vector can be constructed from histogram in a relatively straightforward fashion. Assume uniform distribution within each range of the histogram. Histogram can be constructed by scanning relation or sampling blocks containing tuples of the relation. Skew in range partitioning can be handled elegantly using virtual. Create a large number of partitions, say 10 to 20 times the number of processors. Assign virtual processors to partitions either in round-robin fashion or based on estimated cost of processing each virtual partition. Processor partitioning. Basic idea. If any normal partition would have been skewed, it is very likely the skew is spread over a number of virtual partitions. Skewed virtual partitions get spread across a number of processors, so work gets distributed evenly. Inter-query parallelism. Queries, transactions execute in parallel with one another. Increases transaction throughput, used primarily to scale up a transaction processing system to support a larger number of transactions per second. Easiest form of parallelism to support, particularly in a shared memory parallel database, because even sequential database systems support concurrent processing. More complicated to implement on shared disk or shared nothing architectures. Locking and logging must be coordinated by passing messages between processors. Data in a local buffer may have been updated at another processor. Cache coherency has to be maintained. Reads and writes of data in buffer must find latest version of data. Example of a cache coherency protocol for shared disk systems. Before reading writing to a page, the page must be locked in shared exclusive mode. On locking a page, the page must be read from disk. Before unlocking a page, the page must be written to disk if it was modified. More complex protocols with fewer disk reads writes exists. Cache coherency protocols for shared nothing systems are similar. Each database page is assigned a home processor. Requests to fetch the page or write it to disk are sent to the home processor. Intra-query parallelism. Execution of a single query in parallel on multiple processors' disks, important for speeding up long-running queries. Two complementary forms of intra-query parallelism. Intra-operation parallelism. Parallelize the execution of each individual operation in the query. Inter-operation parallelism. Execute the different operations in a query expression in parallel. If a processor has multiple disks, they can simply simulate a single disk DI. Shared nothing architectures can be efficiently simulated on shared memory and shared disk systems. Choose processors P0 to Pm, where m is less than equal to n to do sorting. Create range partition vector with m entries on the sorting attributes. Redistribute the relation using range partitioning. Each processor Pi sorts its partition of the relation locally. Each processor executes same operation sort in parallel with other processors without any interaction with the others, data parallelism. The join operation requires pairs of tuples to be tested to see if they satisfy the join condition, and if they do, the pair is added to the join output. Parallel join algorithms attempt to split the pairs to be tested over several processors. Each processor then computes part of the join locally. In a final step, the results from each processor can be collected together to produce the final result. For equi-joins and natural joins, It is possible to partition the two input relations across the processors and compute the join locally at each processor. Let R and S be the input relations, and we want to compute R infinitive R. A is equal to S, BS. R and S each are partitioned into n partitions denoted R0, R1, Rn1 and S0, S1, Sn1. Can use either range partitioning or hash partitioning. R and S must be partitioned on their join attributes R, A and S. Using the same range partitioning vector or hash function, partitions Ri and Si are sent to processor Pi. Each processor Pi locally computes Ri infinitive n, A is equal to Si, BSI. Any of the standard join methods can be used. Parallelizing partitioned hash join. Assume S is smaller than R and therefore S is chosen as the build relation. A hash function h1 takes the join attribute value of each tuple in S and maps this tuple to one of the n processors. Each processor Pi reads the tuples of S that are on its disk Di and sends each tuple to the appropriate processor based on hash function h1. Let Si denote the tuples of relation S that are sent to processor Pi. As tuples of relation S are received at the destination processors, they are partitioned further using another hash function h2, which is used to compute the hash join locally. Once the tuples of S have been distributed, the larger relation R is redistributed across the m processors using the hash function h1. Summary. Now in the end, let us summarize what we have learned in this lecture. Database management systems, DBMSs, are complex, mission-critical software systems. The early DBMSs are among the most influential software systems in computer science, and the ideas and implementation issues pioneered for DBMSs are widely copied and reinvented. The client-server model distinguishes between applications as well as devices. Network clients make requests to a server by sending messages, and servers respond to their clients by acting on each. A client computer and a server computer are usually two separate devices, each customized for their designed purpose. Server process is always alert and ready to serve incoming requests. Degree to which system user may remain unaware of the details of how and where the data items are stored in a distributed system. Parallel database systems consist of multiple processors and multiple disks connected by a fast interconnection network. Parallel machines are becoming quite common and affordable. Parallel loading of data from external sources is needed in order to handle large volumes of incoming data.